So I'm going to start recording. So, all right, so we're doing the study set, and that's the answers for the first two. And then this one, we got 1, 3, this is at 5, and then we want to keep going up. So we're going to have a heptanoic acid. 7 is heptane, oic acid, and here at number 5, that would be a methyl. So just be careful, because I saw more than one person did this when we were going through the worksheet during office hour. Make sure that that double bonded O to OH, that has to be your number 1 carbon. If we're doing the numbering, which is what we are doing. Number on D, it showed it as a COOH. I wanted to show one like that. I don't recommend that you write it like that. You wouldn't get full credit from me, because you want to show that it's the O's are not in a row, but that would be carbon 1, and this would be 2, 3, 4, 5, 6, 7. So heptanoic acid again. And at 5, we have an ethyl. So remember, alphabetical order for the side, I'm sorry, that's a 3. So at 3, we have an ethyl, and at 5, we have a methyl. All right, questions? And we're going to draw some. So start at the ending, pentanoic acid. And I, just out of habit, always draw my acid on the right side. That's because when we get into chemical reactions, which didn't show up today, but on Wednesday, there's chemical reactions, because that's esters. It doesn't matter which side you show it on. That's just going to be number 1. And then at number 3, which would be here, hydroxy is an OH. And so if you're doing the zigzags, which I think all of you do zigzags, if you're on it pointing up, your double bonded O points up, your OH would point up. And then here at the carboxylic acid position, that OH would point down. All right. I'm laughing because I didn't look this up, but I'm pretty sure it was 5 carbons. You're not good. Well, you guys, everything's take home anyway. So I would go with the old naming, but if you ran into one, you could always do a quick Google, how many carbons is the lyric acid? And it is 5. So if you did your zigzags like that, where you would have your double bonded O pointing down and your OH pointing up, and alpha means the position next to the carboxylic acid. So alpha is really carbon number 2. So it goes alpha, beta, gamma. And that is the traditional way of naming them. So gamma would be at carbon 4. And traditionally, if you have 2 OHs next to each other, they make one a HO and one an O. That's not a big deal. You do want to, as a question, somebody had asked me last week, it was my other class, you do want the line to go to the O. The H is attached to the O. All right, I keep getting my butanoic acid, do some purple. So butane. And at number 2, which would be here, is an oxo. So oxo would be a double bonded oxygen. So it's just saying oxygen. Hydroxo means hydrogen with oxygen, so that's the OH. And then our last one here, heptene. Oh, and it gave us a cis. So the cis trans can only happen with the enes. So, all right, if you like, you can draw your double bonded O on this side. If you do it on this side, you do need to make this a HO, an HO, so the O is connecting. And that would be our 1, 2, 3. I didn't do a very good job. So this is 3 and 4. And then cis, it would be coming down 5, 6, 7. So ideally, it would have more of a kink. I didn't do my kink so well. You could also start with the kink. probably be a better way of drawing it. Great. All right. Identifying the functional group. I'm going to go ahead and name this. This is an ester because that is your study set for Wednesday. And so on an ester, you always name the side on the other side of the oxygen first. So we just say methyl. It's always going to be something fairly easy to name, like a methyl, an ethyl, an isopropyl. And then the side with the double bonded O gets the numbering 1, 2, 3. You never go across the oxygen. So it's not the longer side gets the numbering. It's the side with the double bonded O, and then you go from there away from the oxygen. So this is propanoate. The side that I circled, it never gets numbers because it's on the oxygen. So again, it's going to always be something that we can name. All right, on B, that is a carboxylic acid. And it's just 1, 2, 3, so propanoic acid. The small, well, actually, I think up through 20 carbons, they all have a common name. I don't remember what a name for propanoic acid would be. All right, on C, this is an aldehyde because it's just a double bonded O, and it has a hydrogen on the bond, on the carbon that has the double bonded O. So this is benzaldehyde. So it's benzene ring with an aldehyde. And then the last one, it's a really funky way, that is a carboxylic acid. So that would be carbon 1. And then we have 2, 3, 4, 5. So 4-methyl pentanoic acid. The thing that's kind of cool at this point, one, like I said, are you really going to be naming organic molecules again in your life after 2 weeks from today? 2 weeks from today is our final celebration, and we're done. It's hard to believe. And but it does give you an appreciation that you never, it's like you never have any issues looking at molecules again. And so it's kind of a game changer. So whatever class it is, whether you remember all the details of naming. The other thing that should be nice with this study set is if you think back to 2 months ago when we would have had our first study set and how it was like, what's a methyl again? What's hex? What are these zigzags? And how far you've come in these 2 months. Melanie, did you have a question?
Yes, I do. So I'm not sure if I have a different, I must have a different worksheet than you. For number 2, I have E and F also. I have isopropanoic anhydride.
Is anything else different?
I don't so far other than that, no.
Okay. So thank you. I must have changed it, and then I found an old copy, and I thought it was, I just looked at it really quick on my screen, and it looked the same. So I can do it. So thank you. This happens every year. I've been waiting, like every homework set, I'm like, there's got to be something I changed, and everybody's being too nice. So what was E?
So E is isopropanoic anhydride.
Oh, that's why. Isopropanoic anhydride. And then you said there's an F?
Then F is acetic benzoic anhydride.
Yeah, I was thinking I had to have an anhydride on here somewhere. All right, so let's do E. So the anhydrides, because there is one anhydride on the worksheet. The anhydride, isopropanoic, you have, that's interesting. It said isopropanoic. I think I got that actually from the book. So the anhydride looks like this. So you have carbon, you have an oxygen between 2 carbons with double bonded oxygens. That's what an anhydride is. This carbon already has 3 bonds, so it only has room for 1 more. So the best that I can guess is that it would have an isopropyl on each side of the anhydride. So this is being named, that's fascinating. This must be a common name for this one. So it's naming it like we would have done a ketone, where you say, okay, this is the anhydride. So the like classic way, or an ether. Here's the anhydride in the middle, and you name each side of it, which is possible because it's like a monkey in the middle. For this one, the anhydride, and again, so you could put the oxygen straight in between, but there is actually that angle. That's what I'm trying to show. So benzene is going to be on one side, and hopefully your benzenes, I know your benzenes all look nicer than mine there. And acetic just means 2 carbons total. So this would just have 1 carbon more, so a CH3. So it's just 2 carbons total. Great questions with that, and that's what an anhydride is. Yeah. All right. So here we go. One question. I know you don't have that on there. So is this the question that's number 4 at the bottom of the page?
Yes.
It is propanoic. All right. So propanoic, you can do zigzags. And again, doesn't matter which side you show your acid. And so NaOH plus the NaOH. NaOH is our base. We'll write NaOH in blue. So it's just an acid-base reaction. So just the hydrogen comes off, and it's going to combine with the OH here. So we would get water as one of our products, and the other one would be the O. I recommend showing the negative so that you know it's ionic. And then the sodium would be there attracted to it, so right next to it. So sodium propanoate is how we would name it. Even if the sodium's shown after, the sodium's just attracted. This is an ionic compound, which comes up on the next page. So propanoate, and then plus H2O. So questions. I just realized who my missing person is, and they're going to want Wednesday also. All right. Let's hope for the best on this back side that I know the pictures are probably the same. Are these questions the same? So the first one is about the gnome, is the one with the higher boiling point?
Yeah, they look the same to me.
Okay. And then the second one is pretty much the same thing, and we're looking at solubility, right?
Yeah.
Okay. All right. So boiling point is, these both have 4 carbons. So ethyl is 2 carbons, and acetate is 2 carbons. This is an ester, and again, you guys haven't done the study set with the esters, but when you go back to study for the final celebration in 2 weeks, which will be on the Monday, yeah, that this you'll recognize that as an ester. So they both have 4 carbons. We're going to pick the butanoic acid because of H bonds. We did a hierarchy last week when I taught this, and so the carboxylic acids were second from the top now, so they're higher than most H bonds. The only thing that's higher is this one, and that's because it's ionic. Ionic is going to always win. And so you see the sodium. All right, on the next one, this guy has an H bond. This one has 2 H bonds. And so 2 H bonds is always better than 1. So double, you can say 2 H bonds, more H bonds, double H bond. All right, the next one is the benzoic acid. So although they both H bond, the acids, because let's just write it like this, they both H bond, but the acid has the extra oxygen. It's actually more complicated than that. It's that the acids can make what's called a dimer, and so they're always bigger than what you think they are. And nothing else does that. It's only the acids. And so since phenol also has an OH, the acid is always going to be higher than an alcohol or a phenol because of that extra oxygen. All right, and then on the next one, they're both carboxylic acids. So we look at size. We're looking for the higher surface area or more carbons, which is the nonanoic acid. All right. All right, so now solubility. I don't like question A, but we'll go with it. I would have to, since it's wanting me to pick one, we're going to go with the one, the H bonds. They both have 4 carbons again. So with solubility, the H bond isn't as big a deal. It's more we're looking for polar, but they're both polar. Then the H bond does get a preference. It also has to do with how esters are with the carbons on each side. It makes it harder for water to find those oxygens that are in the middle. All right, ionic wins. Oops. Double H bond. You guys all see that. There's the OH there and the OH there. Benzoic acid has more oxygens. So again, the acids have that double oxygen, which is going to make it higher than the ones with just one oxygen. They're similar enough size. And then this time, for the last one, we pick the fewer carbons or smaller surface area. So questions. All right. So the bottle test. First one is the acid. So the acid, you can either do, the easiest thing is litmus pink, which is why I'm wearing pink right now, because acids are going to turn litmus pink. Do a pH test. They're acids. That's what that is. Sodium benzoate. This one is going to be water soluble. All of them have 6 carbons. They're all like that 6 carbon. They're probably not really going to be very water soluble or just barely. But this one, because it's ionic, you could also have done the highest boiling point. And the fact that it's ionic, it's probably also the only one that is a solid. The rest would have actually been liquids. All right, where we're going for Wednesday, esters have the most fragrant smell. So this is going to smell like flowers or fruit. So you can't just say something smells good. You're going to tell me what it smells like. So good is actually very subjective. By the way, you don't want to smell for benzoic acid, but the acids and cyclohexanol is actually considered the worst smelling molecule, period, of all the molecules. So when they put these things in, I don't know, it's why you want to stay in school so you don't have to ever be part of this experiment. But what would we do for you don't want to do the smell test and smell which one smells worse, benzoic acid or cyclohexanol. They both smell awful. The ionic's not going to have a smell at all. But for this one, the easiest thing to do would be to oxidize. It is the only one of any of these that's going to oxidize. So remember alcohols, it's a secondary alcohol. So even though our final celebration is going to be on what we're focusing on, the carboxylic acids and esters and the amines and the amides, we will be seeing information from previously, like we see here. There is another choice you have on this one. You could also do Lucas, and so it would turn cloudy with heat. So you do have to tell me what would happen, which is like here, litmus is going to turn pink, because we're going to see another litmus test today, and it's going to be the other color. You could have also, so thinking of that, it was a question somebody asked me the other day, the sodium benzoate would turn litmus blue, because it's actually a base. So questions on that? I can show that on the other side better.
I have a question for 5 and 6. I didn't have time to ask you before you started 7, but how does the H bond influence the boiling point and solubility?
Do you have a specific one you want? Because hydrogen bonds a stronger attraction than just an oxygen attracting to another oxygen. It's like an extreme polar. It's very polarized, and so that's why they made the term up H bond, because it's an extremely polar bond. Does that help? So that's going to show up again tonight with nitrogen. So NHs and OHs make an extreme polar. And actually back to it, which didn't show up here, the ones that have no oxygens, that have no pole, the non-polar, they're always the lowest because there's nothing special about them. They're just like hanging out there unless they get really big, and then with enough surface area. Does that kind of answer what you were asking?
Kind of in a way, but like how does polarity increase its boiling point then?
It's because if they have stronger attraction, so boiling point is we're changing something from a liquid to a gas. And to do that, gases are free. They're just chaos. They're free. They have no attractions. So you have to overcome the attractions. So the ones that are non-polar, this is a really excellent question. So the ones that are just carbon and hydrogen, this is where we're jiggling them apart. So the ones that are just carbons, it's really easy to jiggle them apart. So you don't need much heat to do that. And so as they become more and more polarized, they have more attraction. So we have to jiggle them even more and more and more. So this goes back like when we did the intermolecular forces. And so ionic is the strongest of the attractions. And this goes back when I taught it also, covalent bonds, you can't jiggle them apart. Those guys are attached. And so we're not looking at, sorry, they're cooking something really spicy. And so every time they start heating it, I get all choked up. Yeah, nobody's picked capsaicin. That's what just reminded me of. So does that help a little bit, Philip? That's actually a really good question.
Yeah, it does help. Thank you.
If it shows up on the notes tonight, I didn't give myself much room, but yeah, his question's really important. So the whole idea with boiling point is that we're trying to jiggle apart the attraction between two different of the same molecules. So there's billions of this molecule attracting to itself. So we would just show it as dots. Since there's two H bonds, there's going to be more dots and more connections. And so when you have that extra oxygen, it's even more polarized. So you have an even stronger attraction. Yeah, his question's really important for everybody. With solubility, it's slightly different, but it has to do with that water itself can do an H bond. So it's looking for something that has either an oxygen or an OH. And so that's why the H bond doesn't make as big a difference, because anything with oxygens, but the more oxygens you have, and the H bond means that it has ability to attract in different ways. But surface area ends up being a big factor with that. The other thing I wanted to point out is it was on the previous side. It was something when we did it in the notes. So when you have an acid base, this is the conjugate base. So the salt of carboxylic acid. So the sodium propanoate is a base. And so that's why you could actually do the litmus test. Solubility is a tough one because sometimes they're all pretty soluble. Like this question on C, yeah, you guys didn't do this in lab. That's what makes it hard. That it's a dropwise thing, and so this one you would get up to, you would just keep adding. It would just be completely soluble. Sorry. Whereas this one, probably 10 or 12 drops, and then you would start seeing a separation happening. But it's a really visual judgment thing. Like this one drop, and you'd see it was a separate layer. Like oil and vinegar, they separate the non-oic, one drop, and it would not mix it all with water. The acetic acid, that's vinegar. You can add as much as you want. You just keep adding. Any other questions? All right, I'm going to stop. And